Masana, and this is Lab 3 Black Hole. For part 1 of this lab, we will use a computational model to analyze the motion of a star to find the mass of a black hole, and then in part 2 we will simulate the motion of a spaceship in a figure-8 orbit as its motion is influenced by both a moon and a planet. For a brief preview of the results, this is the mass of the black hole that I found, and this is the initial velocity of the spaceship. Fundamental principles. We have Fnet is equal to dp/dt, and Fnet can be broken down into parallel and perpendicular components, where Fnet parallel acts in the direction of motion, changing the magnitude of the momentum, while Fnet perpendicular acts perpendicular to the motion, changing its direction. So Fnet parallel is equal to p final minus p initial over delta t times p hat, and Fnet perpendicular is mv squared over r in the n hat direction. Next is Newton's law of universal gravitation, which describes the attractive force between two masses, which is given by negative g, which is the gravitational constant, times the product of those masses divided by the square of the distance times r hat. So for part 1 of this lab, we can rearrange this formula to find the mass of the black hole, and then in part 2 of this lab, we will use this formula to calculate all the forces on the moon and the spaceship. Lastly is Newton's second law, which states that the net force acting on a system is equal to the rate of change of its momentum with respect to time. So Fnet is equal to dp/dt, and from this we can get the velocity and position update formulas, which we used in part 2 of this lab to update the moon and spaceship's positions and velocities. For part 1, the system is the star and the surroundings is the black hole. Some assumptions are that the total force is only from the black hole, and the black hole is located at the origin. For part 2, the system is the spaceship and the surroundings are the planet and the moon. An assumption is that the planet is at the origin and is motionless. So for part 1 of this lab is finding the mass of a black hole. We first need to set up our initial conditions, which is the provided mass of the star, and then convert 1 day to seconds to get delta t. Next, for the iteration aspect of part 1, we first calculate the initial and final momentum and velocity vectors right here, and then we need to plug it into the equation Fnet is equal to dp/dt. Then we can calculate Fnet parallel by taking p final minus p initial over delta t times p hat, and then we can get Fnet perpendicular by taking Fnet minus Fnet parallel. And then in line 192, we can find the mass of the black hole by rearranging Newton's law of universal gravitation, which was stated earlier. Now, when we run this code, we can see the star orbit the black hole and end up with a mass of 1.472 times 10 to the 34th kilograms for the black hole. Now, compared to data from background research that I performed on the typical mass of a black hole, this experimental value falls in that range. Now, in these top two pictures, as the star moves closer to the black hole, the gravitational force increases because universal gravitation depends on the inverse square root of that center-to-center distance. And then in these bottom two pictures, Fnet perpendicular is a projection of Fnet onto the n-hat axis, and then the parallel component either points in the direction of motion as it speeds up or points anti-parallel to the direction of motion as it slows down. For possible sources of error, there could be rounding errors when calculating the mass of a black hole. Now moving on to part 2 of the lab, where we must put the spaceship into a figure-8 orbit without crashing. First, we set up our initial conditions, which are the given mass of the planet, moon, and ship, and then we need to set up an initial velocity for a spaceship so it moves in an orbit around both the planet and the moon. So next we create an iterative loop. So first we need to find the force of gravity on the moon by the planet. So the r vector is the position of the moon minus the position of the planet. Then we can use the universal gravitation formula, where the gravitational force is equal to negative g times the mass of the moon times the mass of the planet over the magnitude of that distance squared times r hat. So we can do this exact same thing for Fgrav on the moon by the spaceship, then add these two forces together to get Fnet on the moon. So we can repeat these 3 steps also to find the net force on the spaceship, which we do in lines 86 to 95. Now moving on to lines 101 to 105, we then use the position and velocity update formulas to continuously update the moon and spaceship's position under universal gravitation. Now when we run this code, we can see our spaceship's motion as it moves in an orbit around both the planet and the moon without crashing. So first the moon moves in a circular orbit around the planet, and then after entering the initial velocity of the spaceship, we can see its trajectory is influenced by both the gravitational forces of the moon and the planet. For this case scenario, a figure-8 wasn't possible, but the spaceship's path still reflects the gravitational interactions from both the planet and the moon. For possible sources of error, there could be rounding errors when updating the moon and spaceship's position and velocity. We could also have a smaller delta t to make the calculations more precise. So how is net force and its components different from the rate of change of momentum and its components? They are mathematically the same, but the rate of change of momentum is something that we can more easily measure because we can find mass, velocity, and time. And on the other hand, to calculate net force, you need to find all the external forces acting on the system, which can be more difficult to measure. So what if we wanted to predict the motion of the entire system in a computational model? We would need to calculate all the gravitational interactions between each object using Newton's law of universal gravitation. And since the black hole has the largest mass, it would be the dominant interaction in this new imaginary system, exerting the strongest gravitational force. That is the end of Lab 3. Thank you.